Yes, yeah, we can. You can continue where we left off. The other day, we were doing chemical bonding, right? And we're doing Lewis electron dot diagram, and also we learn how to bond them, how to do the bonding. So we continue, all right? How to bond atoms. We learn about that if you have those outside um, electrons, those we call them a valence electrons, valence share electrons. Those are the ones that participate in the chemical reactions. And then once we get them, then we can um, make sure that they satisfy the octet rule, and then we learn how this some of the electrons can donate or share. The atom can donate or share the electrons. All right. So we did various examples of it, and then we came to a conclusion. All right. So today, I think I gave you guys homework, right? And you guys did the homework. So let's continue. All right. Now let's continue with the ionic bonding. Ionic bond. For example, now I have um, sodium ion, for example, and then you have chlorine ion. All right. And then for them, they want to satisfy the octet rule. All right. So since they want to satisfy the octet rule, sodium on its valence share electrons, like you see, once we have done the electron configuration, this is a neon in a core, and then we have 3s1. All right, so the 3s1 is its valence uh, shell. All right, and now this is chlorine, and then the chlorine to its valence shell is 3s also. So we have 3s2 and 3p5. So these 7 electrons are the ones that are their valence share electrons. All right, the 2 and then the 5. Getting together, adding them together becomes 7. Right, so those are the electrons that are at the outermost. They are out there. So once they are out there, they want to have 8. Right, they want to have 8 electrons. So in the presence of sodium also has 1. Sodium too, it wants to also specify its octet. So it says, like, okay, let me donate what I have. Let me give it to chlorine. All right. So then the sodium will donate its electron to chlorine, like this. All right. So this is a sodium, this is a chlorine. This electrons that is here with the sodium, it will donate it all the way, give it to chlorine. The chlorine will now become an ion. All right, you have a chlorine ion, and then you have a sodium ion. All right. So now both of them have satisfied their octet rule. All right. This is sodium and this is chlorine. Both are ions. And now once they become ions, right? This is sodium becomes positive ion and chlorine becomes negative ion. All right. Positive and negative. And we know opposite attract. Coulomb's law will tell you that opposite charges attract each other, and then the same charges they repel. All right, same charges repel, and opposite charges attract. So once the same charges uh, repel each other and opposite charges attract, they come together. All right. So the sodium ion and the chlorine ion will just attract each other, come together, and form sodium chloride. All right, they form sodium chloride. So that's how, the reasons why, the octet rule need to be certified so that the bonding can, also take place. Is there any question on whatever I've explained so far? If you have any question, let me know and I can explain further. Okay, now let's move on, right? So that's the ionic bonding. So the attraction between oppositely charged ions is called an ionic bond. The attraction between oppositely charged ions is called an ionic bond. Ionic bonds are caused by electron transfer from one atom to another atom. In electron transfer, the number of electrons lost must equal the number of electrons gained. So in any time we do this electron transfer, right, how much we transfer, the electron that we transfer out has to be equal to the number of electrons gained. Ionic bond between magnesium. Now let's see the ionic bond between magnesium atom and oxygen atoms, right? Once we do the electron configuration, all right, we see that the electron share, the valence share electrons of magnesium, becomes 2. To each atom's share has 2 electrons, all right? And then the oxygen to its atom's share has 6 electrons, all right? So then the magnesium, in the presence of this oxygen, is trying to donate its electrons to oxygen. So the oxygen will have 8 electrons. Well, once it's donated, it becomes positive charge, right? The magnesium becomes positively charged, and then the oxygen becomes negatively charged, all right? And like I said before, opposite charges attract each other, then they'll come together and become magnesium oxide and magnesium oxide. So each two ions each have octets as their valence share, and the two oppositely charged particles attract, making ionic bond. All right, so they become ionic bond. So the interaction between sodium atom and oxygen atom. Now let's see the ionic bond between sodium atom and then oxygen atom. The oxygen atom needs two electrons to complete its valence octet, but the sodium atom supplies only one electron. So in the presence of sodium, we have sodium around, and then we have oxygen around. Sodium wants to sodium wants to have satisfy the octet, all right, and then oxygen also wants to satisfy octet. But one sodium atom can just donate only one oxygen atom. Because this noise coming in, so I tried to get rid of the noise. The sodium has one electron to transfer to the oxygen, and but oxygen needs two. So then what will happen? Then we need two sodium. These two sodium atoms to transfer one um, electrons to the oxygen. All right. So then we have sodium oxide. All right. So sodium oxide. So Na2O, Na2O, because you need two sodium atoms to donate their electrons to oxygen atoms. All right. So the need for the number of electrons lost being equal to the number of electrons gained explains why ionic bonds, ionic compound have a ratio of cations to anion that they do have, right? And because of that, those bonds, right? This is required by the law of conservation of matter as well. The law of conservation of matter. That's why we say that, atoms, when you are doing reactions, the atoms are conserved. There's conservation of atoms, all right? Mass is conserved, conservation of atom, but then most are not conserved. Most are not conserved. Yes. So this example says, with arrows, illustrate the transfer electrons from to form calcium chloride, calcium atoms and chlorine atoms, right? From calcium atoms and chlorine atoms, all right? So a calcium atom has two valence electrons. A chlorine atom has seven electrons. So then what do we do? All right. A chlorine atom needs only one more electron to complete its octet. But calcium atom have two electrons to lose, right? In the presence of calcium and chlorine. This one has two, right? That it wants to give out. But chlorine just need only one, right? Just need only one. So what do we do? So then we may have to have two chlorine, and then those two of them can get the uh, the electrons that is being donated by the calcium. All right, so let's see. All right, so the calcium has two electrons, and the chlorine has seven and seven. Just need one and one. So then we need, two chlorine atom to donate to receive the donation of calcium uh, electrons. All right. So when they donate And then this one receives, chlorine receives, they become ions, and then they can bond together to become this thing. I want to give this to you guys for homework, but I still have it here, so let's do it together. With the arrows, illustrate the transfer of electrons to form potassium sulfide from potassium atoms and sulfur atoms. All right. Much the same way, we have a potassium. Potassium has this valence electron is 1, and then sulfur is what? It's 7. All right. Sulfur is 6. So then six electrons. So the potassium, 2 of them will have to come down to give 1 electron to the sulfur. All right. So sulfur has 6, potassium has 1. All right. So each one gives them 1, and then sulfur will have its octet satisfied, and then potassium also have it satisfied. So we need K2S, K2S. So now you see the reason why when we write these chemical formulas, you see some of them are 2 electrons, I mean 2 atoms, some of them are 1 atom, some of them are 3 atoms. That's the reason why, because they want to satisfy this octet rule. Then because of that, maybe you need, for example, a typical example is this: potassium that has to give 2 potassium has to give 1 electron to give it to sulfur for it to satisfy the octet rule. These are fundamental of chemistry, but it's very, very important to understand these concepts so that when you are doing chemistry, you won't find yourself, you won't find it too difficult to understand some certain things. All right. And then we have this ionic strength. The strength of ionic bonding depends on 2 major characteristics: the magnitude of the charges and the size of the ion. The magnitude of the charges and the size of the ion. All right. So the greater the magnitude of the charge, the stronger the ionic bond. Right. So if the charge is big, then the bonding will also be big. And then when the atoms are smaller, they are small in size, then the bonding also become big. All right. The bigger atoms, the bonding becomes, doesn't really bond out as much as it is small. So when the atoms are small, then the bonding is really tight, right? And those that we call we say that is a lattice energy, right? The measured strength of ionic bonding is called the lattice energy. All right. And then this kind of bonding, for example, lithium fluoride has 1,036 kilojoules per mole. Those are its latest energy. It is saying lithium chloride, 856 kilojoules per mole. So those are the energy, right? That gives them that they need to use to bond it, to bond the atoms. All right, sodium chloride, and so forth and so forth. The magnesium oxide. So those are the energies. All right. So these are the homework that I think is in your book. It's in your book, so your model book. So you need to do them. All right. Um. Now we move on to the covalent bonding. Moving away, same bonding, but then for the ionic bonding, there was a transfer of electron from one atom to another atom. One transfers it and one's receive it. All right. And then they become ions. Once they become ions, then they attract each other. And once they attract each other, then they form the bond. All right. Unlike this covalent bond, all right. The covalent bond, in order for them to satisfy the octet rule, they share the electrons. Right. So covalent bond is sharing. Right. Some atoms don't give up or gain electrons easily, right? But what they do, they share the electrons. When they share the electrons, then they also form more. For example, we have this hydrogen, right? Hydrogen needs only two electrons to fill the one s subshell. So each atom has one electron on its atomic shell, which is its valence shell. So then they will just attract each other. I mean, they come together and they say, you know what, you have one, me too, I have one. All right. So then why can't we share? So that you can have two and me too, I can have two. So then they come together and then they share. All right. So then each hydrogen atom will have two electrons on this atomic shell. This is what we call the covalent, I mean, covalent bond. All right. That's how it is. But you can use also dash. That is one. The other side you saw that is two electrons that are put there. You can use dash to represent the two electrons. If it's one dash, that means it's one electron. I mean two electrons. Sorry. But when there are two dashes, that means it's four electrons. When you have three dashes, that means it's six electrons because one dash represents two electrons. All right. And we say that one is a single bond. One is one dash. Single bond. Single bond. We have double bond, we have triple bond. All right. Fluorine atom have seven electrons in their valence shell. So when we do uh, um, we're trying to position them around the Lewis dot electron diagram, and we position them on. You see that there will be one left, right? All of them will pair. One, two, three pairs. One, two, three pairs, right? And then we have one left, one electron left. And what would that one do? Then it also looks for in presence of other fluorine atoms. Say, okay, you know what? This guy has seven, has one left. Me too, I have seven. I have one electron left. The rest of them are paired already. So let me share mine with my fellow, fluorine. So once they share, then both of the fluorines will have eight electrons around their shell, right? That's the outermost shell. So that's how you see it over here. Eight fluorine, eight electrons here, and then eight electrons there in their shell. So the bonded electron pairs make the covalent bond. Now each fluorine has a shell. So they are called the one that are not that don't take part of the sharing, right? We call them lone pair. And the one that take part in the sharing, we call them the bonding pair. All right. So they are called lone pairs. Right. So fluorine atom has one lone pairs. Right. If you go back, let's go to the back. You have three lone pairs. One, two, three. And I have one bonding pair because bonding, that's where they bond pair. One bonding pair. Right. So each fluorine has one bonding pair and three lone pairs of electrons. Right. And so far, what we have shown, I've shown you, right, is when for this bonding, covalent bonding, where they are sharing same type of atom, right, like fluorine, hydrogen, right. There's some point in time, it's not just fluorine, and hydrogen. There's some point in time that there's some other different type of atoms. They can also share their electrons, right? Typical example that we see here is a hydrogen and fluorine. All right. This hydrogen has one electron on its atomos shell. And the fluorine also has seven. It has three bonding pairs. Right. Three pairs. One, two, three. I mean three lone pairs. One, two, three. Then it has one that is not shared. But it needs to satisfy. So then in the presence of hydrogen, then it shares is that one electron with a hydrogen that also has one. All right, then hydrogen will have two. But in the substitution, hydrogen It's only two electrons that it needs exceptionally, right? Two electrons that you need to satisfy is outermost, you know, the outermost shell. All right. Fluorine is eight. So then they share the one one. Once they share the one one, fluorine will have eight, and then hydrogen will have two, and then they are okay. Here you see that is represented by the dot, and then here is just a dash. Dash, like I said before, represent one. I mean, one bonding pair, which is just two electrons there. Another example, use Lewis electron dot diagram to illustrate the covalent bond formation hydrogen bromide, right? So hydrogen, you know, it has only one electron, and let's see bromine. Bromine too um, has how many? Seven electrons. So, okay, let me share with hydrogen. I have one there, and that is not paired. So when I can share with hydrogen, when I share with hydrogen, the hydrogen will have two, and me too. I'll have me bromine. I'll also have eight. Then I'll satisfy the octet. All right, so that's how it goes. Uh, so use Lewis electron dot diagram to illustrate the covalent bond formation chlorine um, molecule. All right, so that's how the answer is. Chlorine bonding together. They have this one has seven, this has seven. They have one left that is not paired. So now they will just share together, and then every one of them will have eight electrons. All right. So more than two atoms to also can participate in covalent bonding. Although any given covalent bond will be between two atoms only. All right. Hydrogen and oxygen atoms forming covalent bond. All right, let's see. Hydrogen has only one um, electron to share. Oxygen has six electrons. All right, it has six electrons. Yeah, satisfy is the once you do the Lewis electron dot diagram, right? It can have two uh, pairs on both sides or any other side, but then it will have one, two lone, on two single electrons on other sides, all right? So once it has that two electrons on either side, then it will need to satisfy its octet. So then it will need a hydrogen, right, to bond with it. But once it bonds with the one hydrogen, it still have one more. But hydrogen just need two. Also, one hydrogen bonds with the oxygen one, then oxygen will have seven. So it hasn't satisfied its octet. Then you need one more hydrogen to also bond with it. So then it has, it will satisfy its octet, right? And then hydrogen also satisfies octet. So let's see. One hydrogen here in six, uh, one hydrogen with one electron, one oxygen with six electrons. So now one hydrogen bonds with one pair of oxygen electrons, and then one left. And over here, the one hydrogen also here will bond with the one electron that is left with the oxygen. Now it becomes two hydrogen and one oxygen. So now you have H2O. So the H2O didn't come just like that. That somebody just said, "Oh, H2." It came from somewhere else. But knowing how to do the electron dot diagram and then trying to satisfy the octet rule to get H2O. All right. So now let's talk about ammonia 2. Ammonia 2 the same, right? And let's see. The nitrogen has 1, 2, 3, 4, 5 electrons. Right, 1, 2, 3, 4, 5, 5 valence shell electrons. And now the hydrogen has 1, 1, 1. So you need three, right? Hydrogen has one electron. So you need three electrons electron from the hydrogen. Where are you going to get it from? It has to come from three hydrogens. All right, three hydrogens. So we have hydrogen, one of them here, one of them there, one of them there. Then they can bond with the 111 electrons that are just there with the nitrogen. So they'll have NH3. NH3, that is ammonia. Any questions so far? Any questions so far? All right, so now let's keep going. All right. This is uh phosphorus uh trichloride. All right. So if you want to bond it, that's how it goes. All right. That's be the answer. So I want you guys, whenever you see something like this, right, you can still go over them to see the reason why it's like that. You just practice it to make sure you know how it is done. All right. So these are the steps to follow. The central atom is usually written first in the formula of the compound. You count the total number of valence electrons. Add extra if the species has negative charges and remove some for positive, every positive charges on the species. Remember when we say it's a charge, positive charge, that means, it has lost electrons. And when it says negative charge, that means the atom has gained electron, all right? Then you write the central atom surrounded with the surrounding atoms. Put a pair of electrons between the central atom and each surrounding atom. Then you complete the octets around the surrounding atoms except for hydrogen. All right. Put remaining electrons, if any, around the central atom. Check that every atom has a full valence share. All right. So these are the steps that you have to go through to get your work done. All right. Now let's see. Write the electron dot diagram for bromine and tetrafluoride ion. All right. So the boron tetrafluoride ion. So the boron atom is the central atom, and the fluorine atom are the surrounding atom. There's an extra electron, right? Because it's an ion, negative ion. So then we count the total number of electrons. Boron has 3 each, and the fluorine has 7. So when you add them all up, you get 31 plus the one that it has gained. So you come 32. Now step 2, you write the central atom, which is the boron, surrounded by the fluorine atoms. So now you are going to put 2, 2, 2, 2, electrons in between the boron and then the fluorine. All right, so that's how you do. So you put 2, 2, 2 electrons here, 2 electrons here, 2 electrons there, 2 electrons there. So them all. So then you have 8. That would be 8, just to satisfy the octet around the boron. All right. So once you satisfy that one around the boron, then you have 24 left. The 24 left, you are going to distribute it among the fluorine. Right? Put two like that, and then it will satisfy it. All right. So that's how it goes. Now the 4 of them have 6. Everyone will have 6 electron. So 6 times 4 is 24, and then there will be no electron left to put in the central atom, and that's it. All right. Now we don't have any other one, so that's how it is done. So covalent bond, right? Sometimes some of the electrons, if you are not careful and you are sharing them, they cannot help you to satisfy the octet. Because if you do that, you cannot really get all the electrons. You can't satisfy the octet. So then you think about, can I have double bond? Can I have triple bond somewhere? All right. Can I have double bond? Can I have triple bond somewhere? So in the case of, for example, CH2O, right? The oxygen and carbon atom share 2 pairs of electrons with the following Lewis electron diagram. So this is the thing. The carbon here, oxygen and hydrogen. Hydrogen, always they have to have just 2 electrons, right? So you can first put a carbon there and then just bond it with the hydrogen. Once you have gotten all the electrons, all right, getting all the electrons, like the steps that we have to go through to get all the valence electrons, once you've gotten them, all right, just bond the hydrogen. Hydrogen will just only have 2 pairs of electrons. So bond the hydrogen and then hydrogen. You bonded them already. So it's satisfied. Now the remaining electron, how are you going to get, you know, 8 electrons around carbon, 8 electrons around oxygen? So that comes to you that you have to just recognize, right? Thinking that, okay, if I make a double bond here, then I can have, carbon will have 8, and then the remaining, I'll put it around the oxygen, then oxygen also have 8. You get it? So this one, there's no any shortcut, but you have to just think and see that, okay, this is the number of electrons that I have. Then if the number of electrons, if you put it like the how we did the boron one, all right, and then it says that, okay, it cannot satisfy the octet rule, then you have to think that, oh, maybe I may have double bond somewhere. I may have triple bond somewhere, right? If you do it double bond, it doesn't work, go ahead and do your triple bond to see whether it will work for you, all right? So that's how it goes. So here, the carbon and then the oxygen will have double bond in between them, and then the rest of them, put it around the oxygen. Then it will satisfy the octet tree, all right? And there's still the bars that I talk about. The double bond will have 2 bars, 1, 2, and the single bond will have only 1, 1. All right? So what is the proper Lewis electron dump diagram for carbon dioxide? The carbon dioxide that we hear every day. What is the proper Lewis electron dot diagram for carbon dioxide? You just count the valence electron. Carbon will have 4 valence electrons. Oxygen, 6. Always carbon has 4. Oxygen has 6. All right. So now it becomes 16. So you have the double bond here. Double bond here, and then oxygen you have 2, 2 there. Then it can satisfy the octet rule. And this one, um, acetylene, right? C2H2 acetylene, right? Nitrogen will have is how many? 5 electrons. And then for nitrogen, one is 5 electrons. So that one, you can just put them together. 5, 5 is 10, right? So put triple bond, and then you have the 2 left. So if you put triple bond here, that means there's 6 electrons. Then 2 of the 4 electrons that are left, you put 2 here, you put 2 there. Then you can satisfy the octet tree. Acetylene, let me come back to the acetylene, right? Carbon 4, hydrogen 2. So first satisfy the 2 electrons with the carbon and hydrogen. The rest of them, fuse them together, in between the carbon and the carbon. Right? So you realize that you have 6. That's the trick. First, do the one that is, for example, this hydrogen inside there. Hydrogen, you need just only 2 electrons. So you just put the 2, 2 between the hydrogen and the carbon, hydrogen and carbon. The rest of them, see if it's going to be triple bond or double bond or single bond between the other atoms. All right. So here it happened to be 3 triple bond. Because once you put here triple bond, then we have 6 electrons. 6 electrons here, and then the 2, 2. 6 here. Here will give you 8, and here will give you 8. All right. So polyatomic ions are bonded together with covalent bonds because they are ions. However, they participate in ionic bonding with other ions. So both major types of bonding can occur at the same time. You can get ionic bonding and can get also covalent bonding. So non-polar covalent bond. We have non-polar covalent bond. The equal sharing of electrons in the covalent bond is called a non-polar covalent. 2 hydrogen atoms involved in a covalent bond, right? The nucleus of both hydrogen atoms attract the electrons by the same amount, right? This creates non-polar covalent bond. We have polar covalent bond and non-polar. Non-polar means, you see the electrons that are outside, right? They will attract, uh, protons and electrons. They will attract. But then if they are the same atom, the attraction will be the same because they have the same number of protons inside the nucleus. So this one will put in the same amount, this one will put the same amount when they are the same atom. For example, we have hydrogen. Hydrogen inside the proton inside the hydrogen nucleus. The proton inside another hydrogen nucleus. And then they have the same strength because they are one and they do attract at the same strength. All right. That's non-polar. They are not polar. All right. But then when you have the polar ones, right, the one has more, protons. The one that has more protons will attract the electrons more to itself, but it's stronger. It has more positive, positive energy. So you attract more. All right. So it then becomes polar because this one it will be more polar uh negative, and the other side will be more positive. All right. So now let's see hydrogen and fluorine. All right. Hydrogen and fluorine. All right. So this hydrogen has only one electron, and then fluorine has seven electrons. Right. That means once it has seven electrons, because uh, it's not really an ion, right? And that means that its um, protons will be the same, right? Protons will be the same. Protons will have seven. Fluorine will have seven protons, and hydrogen will have only one proton. All right. So this one has one, and this one seven. What do you think? What will happen? The fluorine will be stronger than the hydrogen. All right. The fluorine will be stronger than hydrogen. So the fluorine will pull the electron that they are sharing, will pull more to itself. Even though hydrogen also having some of the electron, but then the fluorine will pull more of the electron to itself. So then it become you know negative, more negative, and this one become positive. So we call it partial negative and partial positive. So this is how sometimes we use a tab like this. See here, the hydrogen has a smaller tab here, and then the fluorine has bigger tab. That means fluorine is partial negative and hydrogen is partial positive. Right? The latter is the bonding near to the fluorine atom than the hydrogen atom. Because the electron in the bond are nearer to the fluorine atom, this side of the molecule takes on a partial negative charge, which is represented by del minus. Right? I think somebody's hand is up. Philip, you want to ask a question? You can unmute yourself and
Yeah,
talk.
can you explain the slab there?
The
Between
tab here.
the tab there.
Yeah. Okay, you see what it is, right? You see, it's like somewhat greater than and less than.
Less
All
than
right.
a. Yeah.
Uh-huh. You see, when you are doing greater than and less than, where the maybe five is greater than one, right? You see that the big mouth will look at where five is, and
Oh,
the
okay.
smaller mouth will look at where the one is. You see how
Yeah.
it I remember much the same way. You see the tab
Uh,
there where the bigger part looking is where it attracts more of the electron, and where
okay.
the smaller tab is, the smaller the tip here attract, even though it also attracts electron, but attract is smaller. They
Okay.
get it. So you see
Okay.
how it goes. So where the bigger mouth is, right? So let's when I was learning, all right, nobody when I was learning this, right, I realized that no, you see less than or bigger than, less than or greater than, less than. Okay, okay, where the big mouth is where the bigger number is. All right, same way with this one. Where the bigger tab is, that's where it attracts more of the electron because it has more of the protons inside the nucleus. So because there are more protons, it's stronger. So it will attract more of the electron to itself. You get it? Uh, so then if you don't use the tab, right? If you don't use the tab to show, you can use this there. Right? This is partial positive and partial negative. All right, partial positive and partial negative. So you can write it normal way and put the del plus and del minus. So that's the same thing like somebody who knows it, like how you know it now. Say, oh, okay, it can have bigger tab here and smaller tab. Yeah. So technically, the covalent bond between two different elements is polar, typically. When especially when they have different amount of protons. All right. A covalent bond between two different elements may be so slightly imbalanced that the bond is essentially non-polar. A bond may be so polar that an electron actually transfers from one atom to another, forming a true ionic bond. A scale for judging how much atom of any element attract electrons is called electronegativity. All right. So, Philip, your hand is up. Is it the old hand or the new hand? Okay, I think Philip has, you know. So, a covalent bond, right? A scale. We have a scale that we use to attract. We call it electronegativity. Right? Electronegativity. Electronegativity is a unitless number, right? It's a test whether this bond will be covalent, bond, or this one will be ionic or slightly covalent or whatever, right? You have a scale. And that one, you just have to learn it and use it. All right. The higher the number, the more an atom attracts electron. All right. The higher the number, the more an atom attracts electron. These are the scale. All right. We have hydrogen, lithium, and sodium, potassium, calcium, barium, and all of them here. So you just look at it. Let's quickly take a look at it. Non-polar covalent, right? When it's zero, then the negativity difference is zero, then it's non-polar covalent. From 0 to 0.4, slightly polar. 0.4 to 1.9 is definitely polar covalent. And when it's greater than 1.9, it's likely ionic. All right. So now let's use this as an example to see how it's applied. See carbon and hydrogen bond, oxygen and hydrogen bond, right? We see the electronegativity of carbon, you see the electronegativity of hydrogen, and then we subtract, and then the answer will tell us whether it's polar, it's a polar covalent or whatever. You understand? So for carbon, the electronegativity of carbon is 2.5. Electronegativity of hydrogen is 2.1. So when you subtract it, you get 0.4. Then you go to the chart and check 0. Where does it fall? Right? You go to this chart, you say, okay, 0.4, it falls here. So it's slightly polar covalent. All right, polar covalent. All right. All right. So then oxygen and hydrogen, you know how oxygen is 2.1 and hydrogen is 2.1 and oxygen is 3.5. When you subtract it, you get 1.4. Then you go to the chart again. 1.4, where is 1.4? Okay, 1.4 is definitely polar covalent. But 1.4 is between 0.4 and 1.9. Okay, so that's how you use this kind of scale to check. All right. So you can also, what is the polarity of each bond over here, rubidium, and then fluorine, and phosphorus and chlorine. All right. This is what you have, likely ionic polar covalent. So you can check it, go under the scale and check it to find out how you say it's likely ionic and polar covalent, right? So the polarity of a covalent bond can have significant influence on the properties of the substance. If the overall molecule is polar, right, the substance may have a higher melting point and boiling point than expected. Also, it may or may not be soluble in various other substances such as water or hexane. It should be obvious that covalent bonds are stable because molecules exist. You know. For most covalent bonds between any two given atoms, a certain amount of energy must be supplied. All right. Although the exact amount of energy depends on the molecule, the approximate amount of energy to be supplied is similar. Is similar if the atoms in the bond are the same. The approximate amount of energy needed to break a bond, covalent bond, is called the bond energy. of the covalent bond. Right? You have a bond and then you need energy to break it. Right? It won't just happen just by itself. Just like that. So the amount of energy that we need to use to break the bond is called uh, bond energy. Right? So we have carbon-carbon. This bond energy is 348. Carbon double bond. That one is carbon single bond. You have double bond, have triple bond. All right. So 3837, that's the double bond. We have different type of bonds. Oxygen has the single bond is 146. The double bond is 408, and then the oxygen and then hydrogen has 466. All right. For example, the carbon-carbon, right, single bond is 348. That doesn't necessarily mean that the carbon triple bond will be 348 times 3. No, it doesn't go that way. This was done experimentally, right, to check, all right, to see this one, that how much it is. So you can't do that to say, okay, if carbon double bond is 611, then triple bond just add another number. It doesn't go down. And the bonds involved are just like so. We can say we can also estimate it to find out how much it is. So covalent bond breaking is always an endothermic. Right? Covalent bond breaking is always an endothermic. An endothermic process, right? You make the surroundings, it takes the system takes energy from the surroundings, all right, to use to do the work, all right, the surroundings to use to do the work to break the bond. For example, you have a molecule bonded with oxygen and then with hydrogen, and we want to break the hydrogen, right, off from the molecule and then oxygen. You have 463 kilojoules per mole, right? When making a bond, covalent bond, energy is always given off, all right? When making a covalent bond, energy is always given off. So when you are um, breaking the bond, energy is attracted. You take energy to break it. But when you are making a bond, all right, you give off energy. That one is exothermic. All right, exothermic. That one is exothermic. And when you are um, breaking bond, that one is endothermic, right? So the breaking of the bond, which is endothermic, thermic, right? The delta H, got the enthalpy, like the energy, right? Is positive. It's positive. And when it's an exothermic, the energy is negative. Because it goes away. The energy is leaving the system. So it becomes negative. When energy is coming to the system to do the breaking, it becomes positive because the system has gained energy. So we have endothermic reaction and exothermic reaction, endothermic process and exothermic process. So bonds energy can be used to estimate the energy change of a chemical reaction. So when bonds are broken in the reactants, right, the energy change for this process is endothermic. When bonds are formed in the product, the energy change for this process is exothermic. Combine the positive energy change with the negative energy change can be used to estimate the overall energy change of the reaction, right? The endothermic and exothermic processes that goes on in the reaction, it can really tell us what, how much energy, the net energy, right? The net energy of the reaction. So here, example, we have a hydrogen um, molecule and oxygen molecule combining to form um, two molecules, 2 moles of water, all right? 2 moles of hydrogen, 1 mole of oxygen, these are 2 moles of water. So how do you do about it? So this way they have to break. The bonds of the hydrogen has to break, bonds of oxygen has to break. Remember we said that bond breaking, right, is an endothermic. And endothermic process is positive processes, right? Endothermic process is a positive process. So we take the hydrogen and we break it. Look, going to the chart, looking for their latest energy. And we said, okay, this is how much energy we need to use to break the hydrogen. We are doing the estimation. Then we go to the chart to say oxygen, oxygen. You have 1 mole of it. All right. So then how much energy do I need to attract the system need to get to break the bond between the oxygen and oxygen? All right. Now we have two moles of hydrogen and then two moles of oxygen. That one also they are going to form, right? Formation is exothermic. Like how much energy will I give off when I'm really forming them? All right. So then once I get all those energy, then you know we combine the energies, the positive energies and the negative energies that give us the net energy. So this is how it goes. Hydrogen, hydrogen bond. Go to the chart, find out. Hydrogen, hydrogen bond. Go to the chart, find out. Then we break it. How much energy do we need to break the hydrogen, hydrogen? Oxygen too is a double bond, right? Double bond here, right? Seeing the octet rule, we tell us that okay, the oxygen, oxygen, we have to have double bond inside. So that comes with the knowledge also about knowing whether it's a double bond or single bond. So somebody can just put one bond here and they use one single bond there. But here the case whereby oxygen and oxygen, if you do the Lewis dot diagram and you do the octet rule, it's a double bond in between them. But here, if you use single bond, why is the two going to be? Because the oxygen has 6 electrons on this outermost valence shell electrons, and there are six. So this guy has six. One oxygen has 6 electrons, and the other oxygen also has 6 electrons. They are 12 electrons. If you put two, 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 two here, it will satisfy, right? You need about maybe how many? Two here, two here, two here is 8, and another two will be about 20 of them, 20 electrons. But this, when you put them together, 8 is 16. So what do you do? So oxygen and oxygen, you need to have a double bond in between them, right? So then you go and use the double bond scale, right? Come over here and say that okay, oxygen has double bond. So that's the one I'm going to be using. It's 498 instead of 146 because the single bond is 146. You understand this though, but if you don't understand those Lewis bond electron diagram and also knowing that double bond, and single bond, have different bond energies, then you are going to be in trouble. All right. So when you are doing this kind of work, you have to factor all those things inside. That's why I'm taking my time going over with you guys again today to see that we need to factor all those things in, all right, to get that one. So once you get it that way, then your work will be a bit easy for you. All right. So here, hydrogen and hydrogen, will have once they break, right, then hydrogen and oxygen, all right, will have this bond, and hydrogen and oxygen will have this bond, and the hydrogen, oxygen, because two of them is two moles, right? When you come here, it's two of them, hydrogen, oxygen, oxygen. All right. So then they'll have it this way. So then two hydrogen bonds is 436 kilojoules per mole, and one oxygen double bond is 4 and 8 kilojoules per mole. So the total, right, will be this for the first, the endothermic reaction, right? When we come to the exothermic reaction, right, the bond formation, right, then we have 4 oxygen and hydrogen bonds, all right? Why? Because you go here and you see it's 1, 2, 3, 4, all right? And then the total will be negative 1,852. Then put them together. So then we have negative 482. In actuality, it's negative 572 per laboratory work. It's negative 572. So the difference is just 16% difference, which is not that bad. Yeah, which is not that bad. So we're done with this. Let me quickly go over another slide, and then we'll call it for a day. Uh, so let me unshare this slide. If you have any question, you can ask me before I take these slides off. If not, then I'll take it off. So let me unshare this. Stop sharing. And then Yeah, let's see the intermolecular bonds, right? Intermolecular bonds. Well, like we said before, we have this basic um, bonding. You have hydrogen bond. Right? The hydrogen bond is one of the strongest bonds. As I have liquid, solid, and gas. We know their densities. All right, their compressibility. All right. Um, the gas has its density and has its compressibility. Liquid has its density and its compressibility, and solid also has its density and compressibility. All right. So that one is basic, and then right. Say if the forces between particles are strong enough, the substance is liquid. All right. If the forces between the particles are stronger, the forces become between the particles becomes a solid. If the forces are weak and it has sufficient energy, then it breaks off. All the molecules breaks off, it becomes a gas. All right. So the energy of the particle mostly determines the temperature, determined by the temperature. So is the main variable that determines what phase is stable at any given point in time. So temperature plays a big role. Temperature plays a big role here. All right, plays a big role here. All right. A force present in all substances with electrons in the is the dispersion force. All right. So force, there's this force is present. All right. This force present in all substances with electrons is called the dispersion force. Now, this guy who we came up with it is called London. London. So we can also call it London force. Call it the London force. He described in the year 1900s. This interaction is caused by the instantaneous position of electron in a molecule, which temporarily makes that point of the molecule negatively charged and the rest of the molecule positively charged, right? So the electron is here instantaneously becomes makes that that part that the electron is positioned or negatively charged, right? And the other part positively charged. Then there will be a force, you know, a- a- attractive force between that positively charged position and the negatively charged position. Negative charge position caused by that, instantaneous position of the electron comes landing force. So the greater the number of electrons in a species, the stronger the dispersion force. Dispersion force. This particular explains why small molecules are gases and larger molecules are liquid and solids are the same temperature. All right, because the larger molecules have more electrons. All right, so they are, you have more electrons to have instantaneous, positions. So they will cause more forces because they are more. All right. The smaller molecules, they have less electrons. So then they cannot cause more forces, but they are less. All right. So now let's see. The molecules, the permanent dipole moment express dipole-dipole interactions, which are generally stronger than the dispersion forces if all other things are equal. All right. Then those that have dipole, right? Dipole. The oppositely charged ends of a polar molecule, which have partial charges on them, attract each other. Now, the one that I just showed you, that those um, atoms when they attract each other, all right. Some of them will partially negative and some will partially positive, all right. They will also be attracting, all right. They'll be attracting because this part is partial positive, this part is partial negative. So if there's another partial uh, positive somewhere, there are another atom that has partial negative there, the positive and negative will attract, right? So that's how it goes. So that a polar molecule, such as CH2, Cl2, right? um, it has a significant higher boiling point, which is 313 Kelvin or 40 degrees Celsius than non-polar molecule like CH4, which is 145 Kelvin or negative 128 degrees Celsius, even though it has a lower molecular mass, right? So because of the dipole. All right. So now this is the attraction that I was talking about. This one is partially positive and this is partial negative. Right? So the other molecule or the other atom is partial negative and then it will be attracting to partial positive. All right. And this side will also be attracted to another partial positive atom. An usual strong force, all right, of interaction is called hydrogen bonding. Hydrogen bonding, when it bonds with nitrogen, oxygen, and phosphorus, fluorine, sorry, fluorine, right? It becomes very strong. They are strong. The enough, nitrogen, oxygen, and fluorine, right? It's strong. We call it hydrogen bonding. Hydrogen bond is found in molecules that hydrogen atom with hydrogen atom bonded to nitrogen atom, oxygen atom, or fluorine atom. Such covalent bonds are very polar. They are very, very polar. And the dipole-dipole interaction between these bonds in two or more molecules is strong enough to create a new category of intermolecular force, and that we call hydrogen bond, right? Hydrogen bond. So this occurs between these three um, atoms, nitrogen, oxygen, and then fluorine, right? The hydrogen bond. But they're very strong. So the hydrogen bond is the reason water has unusual properties, right? Hydrogen bonding with oxygen, all right, becomes hydrogen bond, right? Essentially strong. For such small molecule, its molar mass is 18 grams per mole. So H2O has a relatively high melting and boiling point. Its melting boiling point, its boiling point is 100 degrees Celsius. While the boiling point of a similar molecule, H2S, is what? 233 because of the hydrogen bond in H2O, right? This is because hydrogen molecules explain hydrogen bonding, while H2S molecule do not. Uh, so hydrogen bonding is very strong bond. Occurs between the nitrogen, oxygen, and fluorine. Those three um, type of atoms. Right? So hydrogen bond is also responsible for water's ability as a solvent, its high heat capacity, and its ability to expand when freezing, right? So when they freeze, they expand, all right? So when they expand like that, remember, heat density drops. Heat density drops because this density is mass over volume, and then the volume becomes bigger. They create a hole, creating a hole, and then the volume of the you know when the oxygen freezes becomes bigger. The volume becomes bigger. Having the same amount of mass, then it becomes the density becomes less. All right. So the molecules line up in such a way that there's an extra space between the molecules, increasing its volume in the solid state. Right, in the solid state. So here you see the oxygen and then the night, the hydrogen, where the hydrogens are in there and the oxygen are in there. All right, and then this that you create a hole, spaces in there. So there's a white one, is the hydrogen, and then the red one, oxygen, and then they create a hole, two holes in between them. All right, hydrogen bond. So when water solidifies, hydrogen bonding between the molecules forces the molecules to line up in a way that creates empty space. right? It creates empty space between the molecules, increasing the overall volume of the solid. This is why ice is less dense than liquid water, right? The hydrogen bonding forces them to line up, and when they line up, you know, they create a big hole between them. Now, that because of all the results of the hydrogen bond. So identify the most significant intermolecular forces in each substance. C3H8, CH3OH, and H2S. Right? So although carbon hydrogen bonds are polar, they are only minimally polar. The most significant intermolecular force of this with dispersion force. All right, dispersion force. So remember we say dispersion force in all the molecules. They are there in all the molecules because of the instantaneous position of the electrons in the molecule. That's what the dispersion force. Here it's not part of the hydrogen bond because hydrogen, there's no nitrogen, there's no oxygen, there's no fluorine there. So the N is just the dispersion force, right? Let's go to number two, methanol. We have this oxygen and hydrogen, so there will be hydrogen bond in there. So that's good. The molecule has a hydrogen atom bond and an oxygen atom, so to explain hydrogen bond. Let's do the third one. All right, let's go to the third one, hydrogen and sulfur. And right here, you see that hydrogen is there though, but there's no oxygen, there's no any fluorine there. So then the end is what? Although this molecule does not explain hydrogen bonding, the Lewis electron dot diagram and its valence electron pair repulsion indicates that it is bent, so it has a permanent dipole. The most significant force in the substrate is dipole-dipole interaction. All right. All substances progresses from solid to liquid to gas in that order, right? It change from solid to liquid order. Sometimes it just move from solid straight to gas, doesn't pass through the liquid. Sometimes also we move from gas straight to solid, doesn't not go through that. There are names given to them. All right, we'll learn all of them and then move ahead. All substances experience dispersion force between their particles. And we said about this before. All substances experience dispersion forces between their particles. Substances that are polar experience dipole-dipole interaction. Right? Substances with covalent bonds between the hydrogen atom and then the nitrogen oxygen fluorine, becomes hydrogen bonded. Has a hydrogen bond. The first phase of a substance depends on the strength of the intermolecular force and the energy of the particle. Substances can change phase. Right? We know if you have your ice, you take your block from your freezer, ice block, right? It can change phase, becomes liquid, right? It gets energy into it, and then when it is there, it melts, right? It becomes a liquid. So says the ice is solid, right? Typical example, ice is solid, and then one is there, heat comes in there because in the freezer is very cold, right? It's less than 0 degrees Celsius, so it's cold, and it freezes the water, become ice, and when you bring it out, it becomes as time goes on, as heat, you know, going into the ice, trying to establish equilibrium with this environment, um, becomes liquid. All right, so it's melting. All right. Before we used to call it fusion. When you fusion, heat of fusion, but the energy that it gets to melt it is called heat of fusion. Delta H or enthalpy. Right? Enthalpy of fusion, delta H FUS. The subscript is then FUS, fusion, right? So fusion is same thing like melting. So that's how it goes. And then also the heat. Now one is fusing and one is melting, right? One is melting, the temperature will remain the same until it finishes melting. All right. When it finishes melting, then the temperature starts changing, increase. All right. So delta H fusion is always calculated as positive number. Why is it positive number? Because it attracts heat, right? Remember we say it's an endothermic process, and endothermic processes, what we know before, right, is when the species or the system attract heat from its surroundings to do the work, right? So when it gets heat from the surrounding to do the work, then it has gotten heat inside, so it's positive. Right? So endothermic process or delta H fusion is always tabulated as positive. However, it can be used for both melting and solidification. All right, so the same energy, but when it's using to solidify, right, that means heat is being leaving the ice, leaving the water, right? You place the water inside your fridge. You put in that kind of uh, vessel that has that small holes in them. All right, and then pour the water and they want it to solidify. Heat has to leave it before it can solidify, right? So heat is leaving there. So it's a thermic process. So that one you say heat is leaving it because it becomes negative. Heat is leaving the thing. Right? So solidification is always exothermic because it's net, and then so delta H will be negative, right? And then melting, right, is endothermic process. Heat is coming to the system, so it's what? It's positive energy, positive. All right. So water, its melting point is 0 degrees Celsius. That the H fusion is 6.01 kilojoules per mole. Aluminum, 10.7 kilojoules per mole. Benzene is 9.95. Ethanol, is 5.02, and mercury is 2.2 kilojoules per mole. All right, so those are a sample of them. All right. So what's the energy change when 45.7 grams of water melts at 0 degrees Celsius? Water has melted at 0 degrees Celsius. Right? And you have this amount, 45.7 grams of water, and it's melted at this temperature. So what will be the energy? How much energy? We can do the calculations, all right? Because that's 0 degrees Celsius, melting point at the heat of what? The fusion, right? We know it is tabulated, right? So heat of fusion is tabulated at that particular temperature, right? So here water is 6.01 kilojoules per mole. So then we need to change this 45.7 grams into moles, right? That we can use that number. So when we change it, the efficient of 6.010 kilojoules per mole, the quantity is given in units of grams. So you convert the grams moles into molar mass, which is 18 grams per mole, right? 18 grams per mole. Water, hydrogen has two grams per mole. Oxygen is what? 16 grams per mole. You go to the periodic table, you get it from there, and then you say, okay, when I add them together, I'm having 18 grams per mole. So you have 18 grams per mole. Delta H fusion as a conversion factor, right? Then you multiply by it, like this: 45.7 grams per of water times 1 mole of water per 18 grams per mole times 6.01 kilojoules per mole. All right. Then in all, you have 15.3 kilojoules per mole. All right. Um, During melting, right, energy goes exclusively to changing the phase of a substance. It does not go into changing the temperature of a substance. Hence, melting is an isothermal process. Isothermal process. When we say isothermal, we're talking about constant temperature process. Because a substance stays at the same temperature. Isothermal. You have isothermal, you have isobaric, you have isochoric. Isobaric means same pressure. Isochoric means same volume. All right. So when we are doing melting, it's the same temperature that we use there because all the energy that the system is gaining. All right. This is the thermic process. The system is gaining energy. around the system that is getting, and that energy that is getting, using to melt it. It doesn't change the temperature of it. It's after, like I said before, after he has gotten all the energy that he needs, then he use the rest of the energy to change the temperature. Other than that, it will stay the same. All right, it will stay the same. We call it isothermal process. Melting or fusion is isothermal process. Isothermal process. What happens when a solid becomes a liquid? When a solid becomes a liquid. In a solid, individual particles are stuck in place because the intermolecular forces cannot be overcome by the energy of the particles. Right? When more energy is supplied, example, by raising the temperature, there comes a point at which the particles have enough energy to move around, but not energy to separate them. Right. This is the liquid phase. Particles are still in contact, but are able to move around each other. Then you give it more energy, right? Give it more energy, and then they say, "Oh, now me, I have energy." Then I break off. Then it becomes a gas. All right, becomes a gas. So the particles. This explains why liquid can assume the shape of a container. The particles move around and under the influence of gravity, fill the lowest volume possible, unless the liquid is in a zero gravity environment. All right. When you go outer space, then you have no gravity there. But when around here, here the troposphere, right? Around here, we have gravity that's on us. When you go all the way up there, up, past the troposphere, go to the stratosphere, go to the the mesosphere, that one there's zero gravity, right? The process of a liquid becoming a gas is called boiling. The process of a liquid, right? Now we move from the solid phase to a liquid phase, and a liquid phase to a gas phase. All right, a gas phase. So the process of a liquid becoming a gas is called boiling or vaporization. All right, it's typical water. Let's take water for example. We have the water, the ice block giving it energy, then it changes its phase, goes to a liquid phase, and then the liquid phase we have this liquid there. Then you give it more energy, put on heater, put it on the stove, then give it more energy. Then it becomes a gas. The escapes goes to the up. The process of a gas become a liquid is called condensation, right? Vice on the other way, right? Remember, a liquid can become a gas, and a gas also can become a liquid, right? You have vaporization when a liquid is becoming a gas, and condensation is when the gas is also becoming what? A liquid. It condenses to become liquid. That's a condensation. The liquid gas conversion process is noticeably affected by the surrounding pressure on the liquid because gases are strongly affected by the pressure. If you have a gas, we talk about pressure. Like we'll deal with gases on itself, right? We'll talk about those gas laws and I think gas law, Charles laws, Boyle's laws, Gay-Lussac's laws, you know, I mean those laws. All right, we talk about them when we are dealing with the gas itself. All right. This means that the temperature at which a liquid becomes a gas, right? That's the boiling point can change with surrounding pressure, right? Pressure has an effect on the gas. Right? So this gas that we experience on ourselves is atmospheric gas, right? It's an atmosphere. We measure in atmosphere, which is one atmosphere, or 760 torr. Right? There are conversion factors, 760 torrs or 760 millimeters of mercury, right? This in talking about this, right? So the amount of energy required to convert a liquid to a gas is called the enthalpy of vaporization. Enthalpy of vaporization or heat of vaporization, right? Delta H vap, heat of vaporization. The unit of delta H vap is also known as kilojoules per mole. So we need to know the quantity of material to know how much energy is involved. Right? If you don't know, it's delta H per mole. So we need to have the amount, how much quantity that I have to know how much energy I can use to convert it into a vapor. Right? The smaller amount of substance you have, of liquid you have, the smaller energy you need to convert it into vapor. Mind the same if you have bigger energy, right? Bigger, water, for example, bigger liquid. You need more energy to convert it. When you pour water on the stove, you pour water into a bucket full, a big vessel. You need more heat to heat it, more energy to heat it until it vaporizes. It boils and it vaporizes. Much the same way, or conversely, if you have smaller, it will become more. You need some small energy to do it. So the use of data H vaporization, like I said, is kilojoules per mole. Right? Boiling is always endothermic. So S will have positive. Boiling, yeah, it's endothermic. Why? Because you are adding energy into the system. So endothermic. And then condensation is always exothermic. But before you can condense a liquid, all right, you need to take energy from it. And energy going from the liquid is not is exothermic process. So we say that delta H for condensation is exothermic. There's typical enthalpy, right? Substances normal boiling point, right? The endothermic process. Delta H vaporization is 40.68, right? For water, bromine 15.4, benzene 30.8, and ethanol is 38.6. All right. Lady and gentlemen, I know Yara. Yara, how you doing? Yara, is Yara there? Engineer, engineer, Philip, Philip,
Philip is there.
Philip.
Yeah, yeah. I'm
Philip,
sure it's a network problem.
you have a network problem? Oh, okay. NS,
I was
but
saying I'm sure.
are you talking about them? But can they hear me anyway? Because it seems like,
Yes, sir.
but were you hearing me? NS, were you hearing me?
Yes, sir.
Yes, sir. So you are loud
Oh,
and clear.
oh, okay. That's good. That's good. I'll stop here. I'll stop here. We'll meet next week. Next week, God willing. Meet online next week. All right. We'll have to make up, you know, some other classes. Okay. So I'll talk to Kingsley. Kingsley, are you there? Class rep. Class rep.
Sir, please, he had an emergency to attend to, so
Hey, Philip, every day Kingsley has emergency. And he's the one I even communicated with him before the lecture started. And then
yeah, he WhatsApp me to take over, so he
this is what's up you to study. It's not what's up you to take over. Philip, you are studying for yourself. Anyway, I'll speak to him. Okay.
okay, man.
Um, I guess we'll meet next week, God willing, okay?
No,
Enjoy
sir,
the rest of the weekend.
next week we are not meeting.
We don't have meeting next week. Why?
Next week is Easter break.
Oh, Easter break. Oh, okay. Okay, so then the following week we meet, God willing.
Yes.
Sure. I see you guys later.
Okay, sir.
Doctor,
Thank
how are you doing?
Yara, yeah, you come back on it. I was asking how you are
I
there.
was
When
online, but I just left the washroom. I left the washroom. I came back. Then you were calling Philip, calling him, and then you were not hearing.
Oh, okay, yeah. So I didn't know that, you now what it
I
is.
was here.
Uh, okay. I was just because you are the only female in our class, so I was just saying that, oh, it's Yara there, and I saw you. Yara is online, so that's how I was calling.
So
Anyway,
I'm here.
ladies and
you should
gentlemen.
give us the closing prayer.
John
Yeah, give
Kennedy.
us the closing prayer.
The only
You
lady,
know,
the only
you know where
lady.
I am. You guys don't know where I am right now. I'm at Coke. I'm in my hometown. Coke.
You're going to chill for Easter.
No, no, really. I came for a funeral. You understand?
Oh,
Yes. Yes, I'm at Coke. I'm at Coke, Price and ATP. Yes, right now. So I'm calling. I'm lecturing from my hometown. I came with my laptop and everything, and I said, no, I have to meet my student before I come. I go back to
wow.
that. Anyway, I wish you guys, good luck. This Easter, enjoy yourself. Come to Quo and see. Come and enjoy yourself at Quo. You understand? Well, we have at Oyi. No. Anyway, have a nice weekend. Okay, I see you guys
Okay.
later. Okay, bye bye.
Yeah.
Bye.